Hello, welcome to the first lecture of Aerospace and Mechanical Lab 2. Today we are going to talk about buckling of columns, and we will discuss a theory of buckling of columns. But before doing so, I just want to make sure that everyone is on board with the new way we are conducting the labs. So essentially, if you go to your Blackboard, you're going to see these course modules as you saw them in the previous years. When you open each module, you're going to see the lecture notes posted as you did last year. You're going to see the recording and the quiz, and you don't really see this report at the time because I'm waiting for the groups to be formed for the reports, but you see the rest of them. This is hidden from the students, and you will also see this recording posted here on in the buckling module. Essentially, what you need to do is to make sure to watch the lab recording and the lecture recording, which will be named Monday class, before taking the quiz on Friday. And I don't really mind if you take the quiz before or after watching, but these needs to be watched. I will each Saturday I will go to Blackboard and check whether you have watched these recordings, the two recordings I have posted, or not, right? And then that's how you get your attendance. If you come to me and tell me that I didn't really have the time to watch it, and I watched it in the week of the lab, that is not acceptable unless you have communicated this to me before the end of the week. Okay, so I hope everyone knows and understands what is going on here, and let's talk about buckling. Right? In this lecture, we are going to talk about the failure of structures in general. We will do a little bit of review of Euler buckling, and we will talk about lab 1. Okay, so structures can fail in different ways. These failures can depend on the type of structures, conditions of support, kinds of load, and the material used. In this lab, we are going to focus on the types of supports and the type of load that we are applying to our column specifically. So we can prevent failure by designing structures that can bear the failure stress, like the yield stress or the buckling critical load or whatnot, right? So essentially, all of this analysis can inform your eventual design so that the structures that you're designing can withstand the load, right? And can essentially, you can prevent the failure that you're concerned about. The strength and stiffness of the material are important factors in our design, as it was already discussed in the previous lab and also in your previous courses. Here in this lecture, in this lab, we are only interested in the buckling failure. Okay. Before talking about buckling and what the buckling failure is, we need to understand what a column is from the perspective of buckling failure. So we define a column as a beam which length is at least an order of magnitude larger than its other dimensions. Okay, so essentially something like this. The depth and thickness of each beam, the beam, has to be an order of magnitude smaller than the length of the beam. This is called a column. Right? What is buckling though? So if a column undergoes a compressive load, like you see right here, and if that compressive load causes actual displacement in this direction, that displacement, that lateral displacement, is called buckling. Right? You have to keep in mind that the buckling usually happens before the yielding of material. So essentially what it means is if you remove the compressive load, it will go back to its original location. But in most cases, think of water tanks, we cannot remove the compressive load. The compressive load is going to be there, so we have to design for a load that is always present. Okay. The critical load of buckling is the load at which the buckling will occur. So if your load is higher than the critical load of buckling, then the buckling will happen. If it's not, the buckling won't happen. And your job in this lab is essentially to determine this critical load of buckling. Critical load of buckling for this specific for a specific types of columns, right? So there's also a stability discussion when it comes to buckling and critical load. When your load is smaller than the critical load, your column is stable. When your load is equal to the critical load, we are going to have a neutral equilibrium. What does a neutral equilibrium mean? It means that, let's say your column is already displaced a little bit. There's a little bit of displacement already in your column. If you apply the critical load, exactly the critical load, that displacement is not going to change at all. So it won't go back to its original undisplaced form, undeformed form, and it will not deform further. So neutral equilibrium. And if your load is higher than the critical load of buckling, it will keep deforming, essentially. And as I said, in general, critical load of buckling is smaller than the yielding load, meaning that there won't be any elastic deformation if you're just a little above the critical load of buckling. So if you remove the load, it will go back to its original shape. As we can, I guess, understand, the critical load calculation is very important to avoid buckling. We will use Euler's buckling methods. So to be able to use the Euler buckling methods, we are going to make the following assumptions. We are going to assume that our column is perfectly straight. So there is no prior deformations. We are going to assume the material that we use in our column is homogeneous, and our material behaves in a linear elastic matter, which is usually the assumption we make for the material analysis for most of the material courses, like mechanics of material or solids. And we are going to assume the load is applied through the centroid of the cross section. That is not a huge concern because the depth of our column is very, very small. So it's a very safe assumption to make that the load is applied to the centroid of the cross section. And the other assumption is we are going to assume that it buckles or bends in a single plane. So the plane of buckling is not going to change. Whenever you apply a load, it buckles in a specific direction. Okay? And critical load values heavily depends on the type of support you have for your column. Based on this type of support, the critical value is going to change. We are going to have an equation for a specific type of support, fixed support specifically. We are going to see that later on. And then we are going to have a correction factor to accommodate for different other types of support. We're going to see these in the next slide. As you increase the load, the shape of buckling might change. We are actually going to go to the next mode of buckling, as you're going to see here. So this is the equation we use for the critical load of buckling. This is the Euler's equations. N here, critical load. N is the mode of buckling, right? As you increase the load, you see the mode of buckling is going to change. It essentially means that the type of deformation you're going to see is going to change, right? The first mode of buckling, just a regular deformation, and then you are going to see deformation in different directions, deformation in a couple of different directions as you increase the mode of buckling. E here is the Young's modulus of elasticity for this specific column. I is the moment of inertia for the column. L is the length of the column. K is the type of support correction factor. For the fixed support, this K is 1. Okay. So types of supports. So for pinned ends, which means that you are only going to see some rotation at your support. There are not going to be any translational movement, just rotation. Your K is 1. So this equation was developed for this type of support. For a fixed and free end, so you have fixed end, no rotation, no movement, no translational movement, and free movement at one end, no rotation at the other end, free movement, your K is going to be equal to 2. For two fixed ends, your K is going to be equal to half. At pinned and fixed end, so pinned and at one end, pinned support at one end, fixed support at the other end, your K is going to be equal to 0.7. These are the 4 types of supports we have here. Okay, but what does these correction factors mean? Essentially, these are going to change the length of your column to a length that is equivalent to a pinned end support. See, look here. So if you look at just half of this fixed ends column, this half specifically, this is going to behave like a pin end column. That's where the correction factors come from. Let's actually watch this video together to become a little more familiar with the whole thing.
Which column is most likely to buckle? A pin connection on both ends, and this little...
Sorry.
Which column is most likely to buckle? A pin connection on both ends, and this little signal here means it's a pin connection. So you can picture it like a rod being held between your fingers. That's a pin connection. You can kind of pivot. A moment connection on one end and free or no connection on the top. A moment connection on both ends, and a moment connection would be more like a rod being held in your fist. Go ahead and hit pause. The answer is this one, the moment connection on one end and free no connection on the other. So this is a little bit counterintuitive, but there are different ways to brace a column. And we have pin connections, we have moment connections, we have free connections, which are a little bit more unusual, and we have ones that are allowed to translate right to left, and we'll get to those. So if a column is going to buckle, we need to figure out not only the strength of the column and the length of the column, but the type of connection at the top and the bottom is going to kind of govern its likelihood of buckling. Now we're looking at a table, and here you have just different flavors of column. So in A, you have fixed up, top, and bottom. On B, you have a pin connection at the top and fixed at the bottom. On C, you have something that's a rotation fixed but translation free on the top, and something that's rotation and translation fixed on the bottom. On D, we have 2 pin connections. On E, you have something that's fixed on the bottom and allowed to kind of move around at the top. And then on F, we have something that has a pin connection on the bottom and translation on the top. Now, what we're going to need to do when we do the calculation, when we kind of figure out likelihood of buckling, we're going to have to run through a formula, and I'm not going to get into the formula right here, but in that formula there's a value of what's called K, and that K value you'd look up on this table to determine its likelihood of buckling. And a higher K value means a higher likelihood of buckling, because in the formula you're going to take the length of the column and you're going to multiply it by K. So in this one right here, we're going to take the length of the column and we're going to multiply it by 1/2. We're going to multiply it by 0.5. That means from a buckling point of view, this column of, say, 10 feet will behave more like a column that's only 5 feet. If we look at this one here, if we have a column that's fixed on the bottom and it has a pin connection on the top and it's 10 feet long, in terms of its likelihood of buckling, we're going to multiply it by 0.7, so a 10-foot column will look more like a 7-foot column when we size it for buckling. And then this is kind of our baseline. We have pin connections at the top and the bottom, which means that it's rotation free and translation fixed. And that's our 1. So then if we have a 10-foot column, it's going to really behave like a 10-foot column. But look at these two here. These two have a theoretical K value of 2, which means that we're going to have to take a 10-foot column, if we have one of these, and it's going to behave like a 20-foot column. So we're going to multiply it by 2. Now right below that theoretical K value, there's another line that says recommended design value when ideal conditions are approximated. And that basically means we're talking about wood. So the theoretical K value can pretty much work if we're talking about something like steel that's pretty consistent, maybe even concrete that's pretty consistent, but wood is kind of weird. It's got knots and it's got wanes and checks and cups, and no piece of wood is perfect. No two are the same. So in this case, we're actually, in some of these situations, we're going to have a slightly larger recommended K value for wood. So let's go through examples of what we mean by rotation fixed and translation fixed and so forth. So this is a moment connection. We saw this before when we talked about steel. It's a moment connection because we've engaged the flange and the web, and we're holding both of them in place. And so that would be a rotation fixed and translation fixed. It's not going to slide up and down. It's not going to rotate. This is what we called a shear connection before. This one is what we would, in the language of that chart we just looked at, that table we just looked at, we would call this rotation free.
Please enter your remote access
fixed.
code.
It's not able to slide up and down, but even though there are 3 bolts there, it is actually able to kind of pivot.
I'm sorry. There we go.
It's the capital. If we certainly in steel, but remember we talked about buildings kind of sliding back and forth. The 3 bolts are really kind of like a pin. Then we have rotation fixed and translation free. Go ahead and hit pause and try to determine where we use that kind of connection. It's in seismic. So remember we talked about buildings kind of sliding back and forth. And you'll note that we talked about structures in all kinds of other places, right? We talked about it certainly in steel, but in other places as well. So these are the seismic isolations that are in this case, under the Utah State Capitol. If we want something to be able to slide back and forth, that's going to be something we're going to call rotation fixed and translation free. So it can't pivot, but it can translate right to left. Finally, we have our rotation free and translation free. And certainly, of course, a flagpole comes to mind. What kind of works with this at this level? It's kind of rare, and it's not very common in buildings. We sometimes will see it if we have like a single column for a highway overpass. That may behave like something that is rotation free and translation free. Now, I just gave a in-person seminar at AIA New York.
Okay, so it's an introduction to the type of supports. But what you're going to do in the lab, what you're going to see in the lab is this type of equipment. We have essentially different types of supports. You can see this is a fixed support, this is a free support, these are pin supports, and pin and fixed support, and 2 fixed supports. And you have to keep adding weight to this whole system to determine the critical load of buckling, essentially to record the critical load of buckling and compared to the theoretical values, or calculate the modulus of elasticity for this. So 4 different types of supports. You just have to keep in mind that you have to make for each support you have to have a couple of different measurements. You have to do it like a couple of times, not just once, because we are doing experimental analysis, and for experimental analysis we have to be able to repeat our measurements. Okay. This is the buckled version of all of our columns. This is a not buckled version of the columns. And please make sure to watch the recording of the lab, and let me know if you have any questions or concerns.